Hey there, I'm Emily Young from Mind Research Institute. We're a nonprofit neuroscience research and social impact organization devoted to mathematics education. And in the lower left hand corner is my colleague Gigi, the penguin, from our student facing program, ST Math. This is a recording from the virtual conference that Howie put together to bring together our math community and really kind of how this all got started, which is over math memes. So let's go ahead and dive right in.
I've got 3 tens, which is 30, and 5 ones, so that is 30 plus 5. 12 is 1 10 plus 2 ones. Okay, so that's step 1. The next step would be to draw a large box.
So you may have seen this exact meme or something just like it, where the individual on the right goes on to brew their cup of coffee by the time we finish on the left. In the lens of pandemic, a lot of parents have been coming up to us saying, why can't we just teach math the way I learned it? And it continues to perpetuate this debate between teaching procedurally and teaching conceptually. Let's see what Howie has to say about it.
Can we subtract left to right? The answer is yes. Let's take a look. 5 take away 1 is 4, and 2 take away 8 is -6. Now this isn't 4 take away 6. Keep in mind the place value. This is 40 take away 6, which is 34. You can definitely do this with larger numbers as well. Like 2 take away 1 is 1, 3 take away 6 is -3, 5 take away 7 is -2. Keep in mind your place value. So this is 100, take away 30, take away 2, which is 68. Many of us were taught that there's only one way to approach a problem. For example, we can only subtract right to left. But when I learned this strategy from James Stanton a couple years ago, it made me realize that we need to constantly ask ourselves, what if? Try it out and see if it works to show that math is much more creative than what we were taught.
So let's ask ourselves, what if? How can we teach math much more creatively? Generally, when we do that, we ask, how do we teach? But rather, in today's lens of the presentation, I want to stretch us to think, instead of how do we teach, how do we learn? So at Mind Research Institute, we've spent the last 20 years deeply looking into that question of how do we learn? And in the late 1990s, our researchers at UC Irvine were looking into the idea of spatial temporal reasoning and how it connected to music, creativity, and how all those connect to mathematics. And really, the fundamental question we are asking is, what if math could be taught in the way that the brain learns? So I want to dive deeper into this and in the importance of spatial temporal reasoning. Spatial temporal reasoning is the ability to mentally move objects over space and time to solve multi-step complex problems. And spatial temporal reasoning has been shown to be a greater predictor of future creativity and innovation, more so than math or verbal skills. In the widely popularized Purdue spatial visualization test, it found that students in STEM majors, that their spatial temporal reasoning, their conceptual understanding, was the greatest predictor of their success in their STEM field. So when we think about our students and preparing students to be creative problem solvers, the future Googlers and Teslas of the world, how can we help students prepare and get this deep conceptual understanding of mathematics with spatial temporal reasoning? So at Mind Research Institute, we developed a program called ST Math, where the ST stands for spatial temporal reasoning. And we get students as early as kindergarten and first grade expanding their spatial temporal reasoning. It's an area in the brain in which we can all grow, and we're going to do this together now. So some interesting things, ST Math is not like a number of other math programs out there. You'll notice the blue background is designed for calming. There's no distractors for the student. We're just displaying the mathematical problem in a visual way. And all math is boiled down to how can we help a penguin get across the screen? So if I play with these rotations and translations here, we can see the visual and informative feedback as we create our decision. Let's go on to expand our spatial temporal reasoning with a multi-step problem. So kindergartners, first grade, they can surmise that these 3 question marks here means that we're looking for 3 moves to solve this problem. And I want to share one other thing. This time, we don't get that immediate feedback. So if Gigi here, we're looking at Gigi's feet, Gigi's beak is pointing to the left. So if we just would have rotated Gigi, Gigi's now standing upwards. In your mind, what are the next 2 moves we could do to get Gigi standing upright and across the screen? Now I'm not a mind reader. Let's say you chose these 2 buttons. By pressing this green go button, we're going to see the mathematical outcome of our decisions. So close. But this is an interesting point. We get to try this same puzzle again, and based on the feedback that we saw, change the prediction that we made. So instead, what if we used these 3 moves? We're able to help Gigi across the screen. In just that game, it highlights one of our brain's main thinking processes, the perception action cycle. Whenever we're confronted in a problem, and in this case, it was choosing those 3 moves, those rotations and translations to help Gigi across the screen, we use our existing schema, our existing network of neural ideas and how they're connected to make a prediction. We took an action, we chose those 3 moves for Gigi, and we were able to see the outcome as the game animated those 3 moves. Now this is where it gets really neat. Our perception travels to the hippocampus where it meets with our prediction. And when they match, when we were correct, it sends out myelin. It coats that schema in myelin to make it stronger so that the next time we're confronted with a similar problem, we're most likely to reach for that existing network of neural ideas. But let's rewind, because we didn't get the problem right the first time around. We chose 3 moves for Gigi, and we're able to see our outcome didn't quite match what we predicted. And when that perception didn't match our prediction in the hippocampus, it actually sends out theta waves. It signals, I need to learn something new. And when you think of Joe Bowler and productive struggle or learning through mistakes, this is such a powerful learning mechanism that when students can see the difference between their prediction and their perception, powerful learning gains can occur. The reason also visuals work so well is because half of the human brain is devoted directly or indirectly to vision. For most, it's the quickest way to get information to the brain. Unless if we're talking about the olfactory sense, that's actually the quickest. But in terms of math, getting math into the brain, when we're able to use visuals, we're helping our students build that spatial temporal reasoning and creative reasoning skills. Language, it's a great tool, but it gets a little messy. There's encoding and decoding new incoming information. It's a great sense-making tool that when students are starting, they have that existing schema in their brain, they're able to add that language and that academic discourse to latch onto those ideas and expand those connections in their brain. So that's why in ST Math, we use so many visuals first, and then we start to anchor the academic language and the symbols to it. So let's look at this in the lens of what is happening right now. When we think of math as a topic, Generally, it's thought of like this, a list of standards and topics. But when we're thinking about teaching students conceptually and having a deep conceptual understanding of math, what we really want is something that looks a little bit more like this. This is a schema map where the large nodes and the lines show the connections of how different big ideas connect together. And if you're in California right now, this is one of the things that our California math framework authors are talking about in terms of teaching to the big ideas. How can we show students the interconnections between these individual standards? For example, students need to know that multiplication is repeated addition. So if we zoom out, this would be a schema map per se of PK through 8 mathematics and the connections we need to build for students. And if we go back to that first question, new math versus old math, if we think about just teaching procedurally, we're not making those deep connections for students. When we're teaching conceptually, we want to show students the interconnections in multiple different ways in which they can solve a problem. And together, this can build students' deep understanding of math. So I want to dive into one piece of this particularly, fractions, because it's such an important concept and generally where most students struggle early on in their mathematics career. Fractions, it's so important that students get multiple models of fractions and develop that rich schema. So we do this through multiple representations with bars, pies, even triangles in different shapes, fractions on the number line, and even multiple models. When we think of fractions, that scary F word, that's generally where something like this comes up. I'm not a math person. The math gene, that some people are destined to be good at math and others aren't. What we know from the neuroscience is productive struggle, perseverance, and having a growth mindset is what really helps our students for success. So when we think about teaching students just procedurally, this is a question from a recent NAEP assessment, a national assessment taken every 4 years or so that gives a snapshot of how the US is doing in mathematics. It was the subject of a Journal of Science paper, not because students did well, but because students did poorly. Only 1/3 of graduating 12th graders got this question correct, and 1/4 of graduating 8th graders got this correct. When we think about solving this problem procedurally, almost every student in the US has been taught something like this, a butterfly or a crisscross method. But even if students grabbed this procedure and did it correctly, they would get 187 over 104. And it doesn't look like any of these answers down here. Most students answered C or D, adding across the numerator or adding across the denominator. If students aren't able to estimate and visualize that 7/8 is essentially 1, we're going to have a hard time understanding that 187 over 104 is essentially 2. We need to build this conceptual understanding so students can visualize that 7/8 plus 12/13 is essentially adding 2 very similar things. So how do we help students estimate and get this understanding of fractions? This is our game here, GG cycle. Again, we're trying to help GG across the screen by the objects we can manipulate. So I can move this bucket here. Let's just see what happens. Okay, it looks like we got some feedback there. GG rolled out to 1. So we're starting to get a gather here that there's a 1-to-1 correspondence. And we start here from a creative problem-solving place, and then we'll build up to the idea of the concept of a fraction. Now, I do want to note this is a teacher demo platform, We do not scale students up this quickly, and I'll show you that in just a bit. But students don't need the academic language to know this is a half. This game is specifically designed so that students are estimating fractions. So we can move our balloons here. And as we continue to go on, we'll continue to add the symbolic language and even change the way in which we're asking the question to continue to help build students' curiosity and ensure that they know fractions in multiple different representations. So check out this math hack. Pretty neat, right? That game that we just played isn't a math hack. There's a lot that goes into students conceptually understanding fractions. So this is a view into our third grade journey in ST Math. And we have 3 different objections that go align with fractions. In just this fraction concepts alone, you'll see there's 8 different games in this objective comprised of varying mastery levels of over 200 puzzles here. So if you do the math, that means students are solving thousands of non-routine puzzles in just one academic year. So when we think about building schema for fractions, the first thing we need to get correct is helping students understand equal partitioning. Students need to know that fractions are breaking things into equal parts. This is so important. It's the brickwork, the groundwork of understanding fractions. Once we're starting to build that idea, we then take them to this game where students are the ones making those equal partitions themselves. And this is such a great example of spatial temporal reasoning, because if a student can visually recognize that one component is larger than a different component, they're using that multi-step spatial temporal reasoning. Next, we're using some equivalents for balancing fractions. Then there's this game Pi Monster, which students just absolutely adore. You balance the fractions on the back of these pie monsters, and when correct, they turn around and breathe fire. Super exciting. And then we get to this game here, which is really important, where we're starting to make those implicit connections to numerator and denominator. We're actually going to jump into this game here. So here, using this virtual manipulative, students are able to build any fraction. And when I say any, what if we want to see 2/5 as tenths? Students are able to explore the connections between 2/5 and 2/10 and see that on the number line. So when we think back to just teaching students procedurally, we were only on concept 1 of fraction concepts, where we are showing equal partitioning, equivalency, helping students build those fraction models. Why are teachers teaching this butterfly method when it comes to adding fractions? Well, it's quicker, right? It's much easier to teach a standard algorithm than to go through that groundwork of building that conceptual understanding. So why don't we teach conceptually? Well, when we think about it, whatever we're teaching now, the time between the tests that we have is too soon. But when we think about this instead of from a teaching perspective to a learning perspective, when we think about our students, we're not just preparing them for a test. We're preparing them for the world, their future STEM careers. And we want to show them that conceptually they'll get that deep understanding. And I will touch on how that conceptual understanding will improve test scores too. And we'll just remove that little timer because of math anxiety. So this is the quadrant D chart, where we want students up here in this upper right column, where they are solving problems that are rigorous and creative. So on the horizontal axis, we have low-level routine activities like that of a worksheet to high non-routine creative activities. And on the vertical axis here, we have knowledge, low-level regurgitation, and again, where students are really thinking in a creative space. And the difficulty in terms of getting students to that quadrant D is most of our academic curriculum items are here. And I'm not banning worksheets, they are certainly useful for practice. But when it comes to helping students build that conceptual understanding, a lot of times the way we try and get to that quadrant D, that rigorous problem solving, is through a word problem. What ST Math does is for all students without the barrier of language is getting students solving problems in that rigorous problem solving zone. And by doing so, by having low floor, high ceiling activities, we're able to keep students on grade level. So this here is a 2-year study in Texas. And in ST Math, we have over 120 efficacy studies, Mind Research Institute, where research is literally our middle name. We can show that teaching conceptually improves the outcomes for all students. It's a cornerstone of an equitable teaching approach. All students and teachers would love to have 91% of their students meeting or exceeding standards. But with ST Math, they were able to go further. And we see this for special education. They over doubled their outcome on ST Math in terms of not having language and other barriers to math. Additionally, we're able to keep all students on grade level with ST Math. You'll see here, even if a student was 1 year behind, 2 years behind, or 3 years behind, the difference is time. They just needed more time to get through the curriculum. And by starting games from a place of a concept that they understand and adding that connection, we're able to build that understanding in mathematics. So often we leave our students with an impression of math as a field as really something they're not using often in their day-to-day life or real-world math. I want us to think back to really how the field started. Take a look at this image. It's a computing division where instead of computers, the humans are the computers. Think about that one. This is an image from NASA, and this quote is just so powerful. The volume of work often necessitates computers who can perform routine machine operations with great speed, but who need not have much logical insight into what the results should be. That's a quote from NASA. Just think about that. Need not know what the results would be. When we think about the old way of teaching math, it was to make it so you do it like a machine. You could do it quickly, effectively, but you need not to know how come or why it happens. When we think about the tools we have now, we need math as a creative problem-solving tool so we can prepare our students to build machines. At Mind Research, we are so passionate about preparing the next generation of students to solve the world's most challenging problems. So when we think about the lens of our future, how should we teach? And I want to leave you with this. I hope not only can we make problems more realistic for students, but we can show them that mathematics is a beautiful and creative subject that connects throughout all domains that they can use to solve the world's most challenging problems. Thank you so much for joining me for Math versus Memes. I look forward to connecting with you. Thanks so much. Don't know how to stop the recording, so we will stop it here.